Section 8.7. The vapor pressure of a pure substance depends on the applied pressure. So it tells you if you have pure water, you have liquid and vapor coexist. And then if you add a lot of argon to the system, or helium, whatever, high pressure helium, high pressure argon, that will slightly increase the water vapor pressure. Why is that? First, adding argon or helium does not change the chemical potential of water vapor because they are noble gases. There's no interaction between helium and water molecules in the gas phase. But adding argon or helium will slightly increase the chemical potential of the liquid water. Why is that? Because dG equals negative SdT plus VdP. Remember? The chemical potential of water is molar Gibbs energy of water, and then it's negative molar entropy dT plus molar volume dP. So the chemical potential does depend on pressure. And this pressure is the external pressure the liquid feels. So if you add argon or helium into the system, the liquid feels higher pressure. And then the chemical potential of the liquid will increase, but slightly, because the molar volume of liquid water is very small. It's roughly 18 milliliters per mole. So, by the way, if you change the pressure from 1 bar to 2 bars, the difference is 1 bar. Use 1 bar times the molar volume of water, 18 milliliter per mole. What's the result? The result is 1.8 joule per mole. That's actually a very small change to the chemical potential. 1.8 joule per mole is very small because the enthalpy of vaporization is 40,650 joule per mole. Okay, 1.8 versus 40,000. Now let's look at the math. So let's say we're looking at this picture. And let's say if we have a external pressure of 1 bar and this is the room temperature. Okay, water exists in the liquid phase. On a 1 bar pressure, room temperature, the liquid is most stable. If we reduce the external pressure to 0.0316 bars at the room temperature, the chemical potential of gas and liquid are the same. So you have liquid water, you have 0.0316 bars of water vapor inside. Now this time it's going to be interesting. Over here, we change the external pressure back to 1 bar. So very high pressure. But this time, we're using argon, so we're cheating. So really in here, this water pressure is still roughly 0.03 bars. The remaining is from argon. The argon has a 0.97 bars pressure roughly. Okay, now let me show you some theoretical derivations, some calculations. So we learned this before. The chemical potential depends on pressure. The dependence is just the molar volume. So I want to show you this notation. Okay, so this is in both font. This is the total pressure. This is the pressure of water vapor plus the pressure of argon. So this is just the water vapor pressure. That's the big difference. All right. So the chemical potential of water vapor depends on the water vapor pressure. The chemical potential of liquid water depends on the total pressure exerted on the liquid surface. So this is both water and argon. All right. So very important. And then we do the math. We start from a initial state, which is just pure water. Pure water at 298 K, 0.0316 bars. You have liquid, you have gas, they coexist. So that's our starting point over here. That's our starting point. That's only water. So this is water vapor pressure, but also the total pressure is the same. Now we're going to change the pressure. All right, we're going to introduce argon. So this is argon. We're going to introduce argon. So this is the final water pressure. Final water vapor pressure plus the argon pressure. That's the total pressure exerted on the liquid. That's why we're integrating this for liquid. And over here, this is water vapor pressure. This is also water vapor pressure, but this is after the introduction of argon, and this part is the molar volume of water vapor. So we just need to integrate this too, and then we can solve for this P sub F. So let's try this. This guy is roughly a constant, so we take it out, and it's just the final total pressure minus the initial pressure. Over here, this is RT constant, 298 K, and then the integral of dP over P is LMP, so we have LMP final over P initial. Again, this is just the water vapor pressure, and then we just need to solve this. If you use 1 bar argon pressure, put 1 bar here. If you use 10 bar argon pressure, put 10 bars here. Anyway, just solve this. Let's look at 1 bar first. Okay, let's say we introduce 1 bar argon pressure, and then we plug it in. We solve this equation. The molar volume of water liquid is roughly 18 milliliters per mole. All right, so plugging on the numbers. Let's look at this Wolfram alpha. So again, I'm just too lazy to even use a calculator. This is the molar volume of liquid water. This is the pressure of the water vapor after the introduction of argon. This is 1 bar argon. This is the initial pressure of water vapor, 0.0316 bars. So I'm using bar here, bar here, bar here, and then I convert bar to Pascal here. Over here, this is R times T times the logarithm of the final pressure in bars over the initial pressure. And this final pressure, again, this is the water vapor pressure. So let's look at the result. It's right here. It's 0.03162. Right over here. What's the initial water vapor pressure? 0.0316. After you introduce 1 bar argon, the water vapor pressure increases by just a tiny amount because the pressure of argon increases the liquid water chemical potential by a tiny amount. We can add more argon. Let's add 100 bars of argon, plug in the same equation. Well, this time the water vapor pressure is a bit higher. It's 0.034 bars compared to 0.0316 bars. But this time we really made a lot of effort. We added 100 bars of argon, but yet its impact on the liquid water is very small because the molar volume of liquid water is very small. So again, if you multiply this 100 bars with the molar volume of water, 18 milliliters per mole, what's the result? The result is this is 100 times 10 to the power 5 pascals. The molar volume is 18 times 10 to the power of negative 6 milliliter per mole. So when you do the multiplication, you will get 180 joule per mole. It's still very small. 180 joule per mole. It's 0.18 kilojoule per mole. The vaporization of water has an enthalpy change of 41 kilojoule per mole. So compare 41 and 0.2. All right.